Hey everybody, welcome to another CSVO2 assignment. For this assignment, we're going to implement, I suppose, this automated menu ordering system for the Krusty Krab. So Mr. Krabs, he is coming out of the past and into the present, which I believe there are fast food restaurants that have an automated ordering system for some reason. I mean, it makes sense. I mean, you already are in the restaurant, so why not talk to somebody instead? No, let's just go ahead and use an automated system instead. I totally get it. As you can see there, SpongeBob, right there, he discovered not a boulder, but a rock, which he of course, can use to deliver the first Krusty Krab pizza. Luckily for our assignment, we're not going to have anything that intense, like delivering a Krusty Krab pizza, just a regular ordering menu system. Now, for this assignment, we're going to implement our own custom hash map class to be used for looking up and inserting elements. And remember, hashing is a fast way of searching for a collection of data. So we'll be using that to implement this menu. Let's go ahead and now discuss the hash map class. So I have our description of our class here in the PDF. And also I will provide you with a header file in this assignment. And I also will give you the implementation file where all of the function headings will be given to you, but you have to fill in the blanks and implement each function. But I do give you the function headings just because it does make it easier somewhat to compile. I know with templates it can be a little bit challenging, so for that reason I do give you the skeleton. You have to just fill in the implementation of each function. So our hash map class, this picture right here, is a good visualization of how we can look at our hash map. It's going to be somewhat of how shall I say, a modification of open addressing. So we're going to have two tables instead of one, and each table we're going to have at most one node stored in each table. So just refer or sort of think of the example where if you have a parking lot can be like one giant table, and each parking spot has some index, and each parking spot can contain at most one car. So in this case right here, for table 1, at index 0, there's no node here, so we would actually store a null pointer in this spot, which would denote that this location is blank. There's nothing actually stored there. Then table 1 at index 1 contains a non-null pointer. It contains the address of some node in this structure. So each node contains a key value pair. And notice in table 2, at index 4, there is nothing there, so it would store essentially null pointer, implying there's nothing in this location. And table 2 at index 3 contains this address, a non-null pointer, implying there's something there. This node represents some object stored in this location. So each node, going to this PDF for a second, each node contains a key value pair, T1 key, T2 value. And notice how there's no node star link. And the reason why is because, well, we're not going to have a linked list. We're going to have at most one node. So there's no reason to really have a node star link to the next node in our linked list. And then, of course, we have our two constructors to make it easier to initialize the object when we allocate a node for this table. So we have here node star table 1, node star table 2. Those are going to be our two tables, essentially. So we're going to have a modified version of double hashing, essentially. But I do give you the mechanism of how you will double hash in the PDF. But of course, I will also do a visual in this video as well to help you see how it's going to work. And then we have these two variables, items 1, items 2. That's going to be a count that tells us how many elements we have stored in table 1 and table 2 respectively. So right here in this example, Table 1 has only one element stored in it at index 1. So items 1 will have the value 1, implying there's one element stored in table 1. For table 2, we have also only one item stored in it, so items 2 will also contain the value 1. And we always increment it by 1 every time we insert something into table 1 or table 2 respectively. The capacity will tell us how many elements we can store in the table. In this case right here, the capacity in this example would be 6. We can store 6 elements in table 1 and table 2. So table 1, table 2 will have the same capacity, so it's more uniform to make it a bit easier, although we could have these tables be a different size, but just to be simpler, we'll just have capacity will be just one variable, and both table 1 and table 2 will have the same capacity. So now we have our two hash functions we're going to use, and they're relatively simple to implement. Let's go ahead and scroll down the PDF. So before I even do that, we actually use a string as our parameter. And the reason why is because we can't really make hash 1, hash 2 really a template, because we have to kind of know the key's data type in this case. And for this example, we can imagine that the key will always be a string type. And also, to go on some tangent here, we include menutype.h in this file. So we're going to have the value is going to be menu type will be the value, and t1 will be the key type will be a string. So it's going to map a string to a menu type object. Now, it might seem a little bit overwhelming, but for now, for the examples we're going to be talking about, we'll just have it as t1 will be a string and t2 will be an integer to help us understand. But in reality, if t2 were to be maybe a menu type object instead of a primitive type int, it doesn't really increase the complexity to implement this class. But so if you're able to get this to work with integers, in reality, it shouldn't be much of a problem to get it to work with custom types. Okay. So here's the description of our class, and here's our two hash functions defined right here. Let me go ahead and show you here on OneNote as to what I mean by these. So this will be our hash function 1. So suppose the search key, the string we pass in, happens to be the string hello. Hash function 1 will take the ASCII value of h, multiply it by 10 to the power 0. So since h is at index 0 of the string, plus the ASCII value of e multiplied by 10 to the power 1, plus the ASCII value of L multiplied by 10 to the power 2, and so forth. This summation, this expansion sort of models a summation. We add this up and return that sum. That's it. And the purpose of doing this, so the purpose of having this multiplication by 10 to the power I, the purpose of this is, suppose we have anagrams of our strings. Then if you have an anagram, then we're not going to end up having two anagrams both give us the same result. If that's the case, then it's going to, of course, cause a collision in our table. So you want to make sure that we don't have any collisions. So we'll use this as a way to create larger values and to also not have the same result for anagrams. For hash function 2, it's going to be sort of the opposite. So we take, in this case, capital H multiplied by 10 to the power 4 plus capital E, plus lowercase e multiplied by 10 to the power 3 plus the ASCII value of L multiplied by 10 to the power 2, and so forth. We sum these up and return that. So it's really just the opposite direction. So these two summations are kind of modeled right there. I think they're rather simple to implement. So that'll be your hash function 1, hash function 2. So we have the resize function, which I'm going to talk about that in a little bit. It's going to be used when our table starts to get rather full. We want to resize it. And then we have our lookup function. This is going to essentially be the heart of this hash map class, because we're going to be using this lookup function to find the index of where we're going to either, of where the element should be or where we need to insert into our table. So this lookup function returns an index of where this k parameter either is or should be in table 1 or table 2. And again, I will spend some time discussing the lookup function in a little bit. Let's go ahead and go through our public members next. So we have our constructor, which is going to be a parameterized constructor, but we assign some default value. I'm going to choose 7 in this case. So this value 7, we're going to assign that to the capacity field of our class. In the constructor, we're going to set items 1 and items 2 to both be 0 because our table 1 and table 2 will be initially empty. We're going to allocate an array to table 1 and to table 2 of length capacity, or length 7 in this case. And we have to assign each element of table 1 and table 2 to be null pointers. So we allocate an array of node pointers to table 1, and we also allocate an array of node pointers to table 2, and we assign all null pointers to every element in these two tables. And that's all what the constructor does. The destructor, well, of course, will deallocate the object. So the destructor in this case, well, we can't just simply just deallocate, so to say, delete bracket table 1 and then delete bracket table 2. We have to, of course, deallocate each of these nodes. So you have to traverse table 1 and table 2. And for each location is not null, we have to deallocate each node independently and then deallocate the entire table. Same thing for table 2. A little extra work, but it's similar to deallocating in a two-dimensional array. Same concept like that. So now we have the rest of our public functions. We have our find function. We pass in some key. It returns true if this key was found in my hash map, and returns false if it wasn't found. Insert function, we pass in our key value pair. Insert function will insert a new node in table 1 or table 2, and it will assign the node's key field with k, and assigns the node's value field with v, which is parameter v. Update function, similar idea. It will find a node with the matching key, and it's going to reassign the value. And in GetValue function, we pass in some k parameter. It will find that node with the matching key, and it returns the value field. So that's a rundown of our hash map class. Let's go ahead and now discuss the lookup function, how it can be used in our find, insert, update, and get value functions. Okay, so I have the lookup function defined for you right here in the PDF. It's just sort of just a double hashing technique. So we take our hash function 1 of k plus I times hash function 2 of k, take that sum, modify capacity, where I is going to be some collision encounter. So it's going to essentially be set to 0 initially. So you can imagine that you would define I as a local variable in the lookup function. And we compute the index. What we have to do is we go to table 1 at this index. If, let's say, it's a null pointer, return the index, which means that location so table 1's index is a null, that means this element has not been inserted in our structure yet. So return the index immediately, or return at that point. If this location, table 1 at this index, is not blank, but a matching key, so that node at this index matches our k parameter, return the index. We found the index of where the element is. If, let's say, table 1's index is not null, and it contains a mismatching key, we have a collision, so we try the same index in table 2. And same idea. If table 2 at this index is blank, return the index. If it's not blank, but has a node with a matching key, return the index. If that table 2 at the index also has a node with a mismatching key, we have another collision, we increment I by 1, recompute this new index, and do the same thing again. That's sort of the concept, or sort of the mechanism for how we're going to search. So now, of course, you read that PDF. I read that PDF out loud for you. Let's go ahead and do an example as to how this is going to work in a more visual way. Okay, so Suppose we define our people map like this. We have a string to int mapping. So for this people object, we have table 1 and we have table 2. And their capacities are both going to be 7 in this case. And we set every element in table 1 and table 2 to all be null pointer. And we set items 1, items 2 to both be 0. And our capacity will, I didn't put it here, but our capacity would be 7. So let's go over how we would insert elements into our map. So I'm going to try to sort of have 2 layers here. So we're going to first, let's say we call people.insert, and I'm going to pass in Alice and 12. So I want to insert this pair. I want to insert a node that will have key Alice and value 12. So you can imagine inside of our insert function, what we're going to do is perhaps we can define some index variable. I'm going to call LookUp inside of this insert function. And I pass in Alice because Alice was passed into the insert function. Now let's go ahead and now enter in the lookup function, see what lookup function is going to do. Okay, let's say for lookup, we will create a variable. Suppose it will be size t, and I'll just say x for right now. And suppose x is going to be our index in this case. So I'll call hash1 pass in Alice plus 0 times hash2 pass in Alice, modify capacity, and suppose this lookup function, let's suppose x will have the value 4. It computes the value 4. Okay, so we have to see what is at index 4. So we're still in the lookup function currently. Index 4, we see it has a null pointer right there. So we don't know. Lookup function does not know if it was called within the insert, find, or get a value. So right now, we don't know if we're trying to insert or find something. Either way, if let's say we compute 4, which we just did right now, suppose we compute 4, what's going to happen is index 4 of table 1 is null. So that means that Alice cannot be in our table. Because if Alice were in our table, either index 4 would contain the node Alice, which means we have a match. Now, if let's say index 4 had something else, a node with a different key, let's say, well then, of course, we have to check table 2 at index 4 and see what's there. So since index 4 was a null, that means table 2 index 4 has to also be a null. The only way index 4 could contain something is if table 1 index 4 had something else. So the fact is that since table 1 index 4 is blank, that means Alice cannot exist in our table. But index is going to return back to us either a match of where it found the record, or it's going to return the index of a vacancy. So if it was called the insert function, we know to insert at index 4. So lookup returns 4 because in a lookup function internally, it calculated 4. Table 1 index 4 was a blank, so we can return 4 immediately. Now, going back to the insert function. So lookup function returns 4 into our index variable. So we have to, again, go to index 4 and insert. Index 4 is blank, so we can insert Alice at index 4. So I'm going to go ahead and just insert a node right here. And I'll assign the key to be Alice, and the value will be 12. And I'll update the items count, which was 0, to now be 1. Okay, let's go ahead and insert another name. And this is going to be a very bad example, but I want to show sort of what happens in this extreme case so we can try to understand how the insert function works. So let's go ahead and call insert. I'll insert Bob this time. So you have the classic Bob and Alice. And I'll assign 20 to Bob. Okay. So the first thing we have to do is so we're right now in the insert function. The first thing we have to do is we're going to have some local variable index, and we're going to call LookUp and pass in Bob. Very well. Let's go ahead and just, now let's enter the lookup function. So right now in lookup, the first thing we'll do is we will create this variable x, and then we apply this calculation right here, like in our PDF. And suppose we calculate 4 initially. So the first thing we have to do is go to our table and see what's up. So we first go to table 1 at index x or 4. So index will be x in this case. Index 4 contains a non-null. It's something there, but it's not Bob. So we have a collision. So now we will try table 2 at index 4. And right here we have a vacancy. Okay, so that means that we want to insert Bob here. So the lookup function, it returns the index of where either it found a matching key in either table 1 or table 2, or it returns the index of where it found a null in table 1 or table 2. Okay, so now we return 4 back to the insert function. The insert function called lookup, it received 4, so we're going to go to index 4 and see what's going on. So table 1, index 4, contains a non-null, contains a node that contains Alice. Okay, we have a collision. So that means lookup function return 4. That means we know index 4 would have to be a vacancy in table 2. So we go to table 2 at the same index and we see, oh, we have a vacancy right there. So we're going to insert Bob right here because we first tried table 1 index 4. We had a collision. Using the same index 4, we tried table 2. Table 2 index 4 is blank, so we can write Bob right here. Or we can store Bob, sorry, right here. Okay, so that's the idea. Now, let's say if I were to do a find or a get value for Alice or Bob, what it will do is it calls lookup function. Lookup returns 4. So let's say I wanted to do this. Let's just do this for a second. Let's say I want to do cout people dot get value Bob. Let's go through the same process again. So the get value function, similar to insert, the first thing we'll do is call lookup. Now it returns 4 again, but let's go over and see again how lookup is going to once again compute 4. So now we're in the lookup function, and we apply the same technique. We take a hash function 1 on Bob plus 0 times hash function 2 on Bob. We compute that result, modify capacity, and it happens to compute the value 4. So we're going to go to index 4. In table 1, we check. Index 4 contains a node, it's not a match. Okay, let's try table 2 at the same index. It contains Bob, so we found Bob. So let's go ahead and return 4 back to the getValue function. So the getValue function right here receives 4 for the index and does the same exact, look through. It's going to go to index 4 of table 1. It will see that index 4 of table 1 is not a match. It tries index 4 in table 2. It checks the key. It matches Bob. It returns 20. And then in main, it outputs 20 because the value it returns is 20 because we found a node that matched Bob, and it returns 20. That's the value associated with Bob, as you can see right there. Okay, let's go ahead and now just try another example where something crazy sort of happens, or something a little bit bizarre. Again, this is very unlikely to happen, but we want to cover this extreme example so we get the whole scope of this. Let's go ahead and try to insert another name. So I'll insert Joy 22. Okay, so for insert function, we have to call our lookup function, because lookup is going to tell us where in table 1 or table 2 should we insert Joy. So I'm going to call lookup, and lookup does all that heavy lifting for me. Okay, let's go through the steps as to how the lookup function works for the name Joy. This is actually, so again, this is not the actual what the hash function 1 and 2 are going to do. I'm just sort of making up values here just to sort of test out how lookup happens to find the indices of where the keys are or where they need to be inserted. So again, this is not realistic based on the actual hash function, but just let's pretend it gives us these numbers. So let's go ahead and enter the lookup function. Let's, for the heck of it, just say that, okay, it computes 4. Again, it's 4, we're picking on 4 quite a bit. Okay, let's go to index 4 and see what we have. So table 1, index 4, is not null, and the node at this location contains Alice, not Joy. Okay, let's try table 2 at the same index 4. Table 2 index 4 contains Bob. Okay, so that means Joy was not index 4 of table 1 or table 2. So we have a collision in both tables. So now we're going to increment our I counter by 1 and then recompute the index. So suppose when we recompute the index, in this case, let's say we recompute 1. So doing some calculations, just pretend for right now, we compute the value 1. Okay, let's check and see what what happens now. So we go to index 1 in table 1, and we have a vacancy right there. So that means that Joy is not in our table. If Joy would have been in our table, Joy would have been either at index 4 of table 1 or 2, or in this case, at index 1. So since index 1 is a blank, Joy would have to naturally go right here. So we can return 1. That tells the insert function to go to index 1. So in lookup, we went through all this process and we finally return 1. So going back to the insert function, lookup returns 1. So we go to index 1 in our table. It's a blank, so we can write Joy right here. So I'm going to store the key, will be Joy, and the value I believe is 22. And items 1 now contains 2. We have 2 items stored in this location in our table. So lookup function does all the actual work. And we go back to the insert, update, or get value. We just sort of have to blindly trust that lookup function worked correctly. So when lookup returns back to us, we just simply check in table 1 and then table 2. That's all. We don't really have to worry about doing all that linear probing, or sorry, we don't have to probe the table. All that probing is happening in lookup. Insert, get, and find. It's doing all of that. It's just simply calling lookup, and then lookup will tell the insert function which location to look for in table 1, table 2, and that's it. So for example, let's say I wanted to find Joy. I want to output Joy now, let's say. Let's output people.get value Joy and L. So we have to get the actual index. Now, let me just sort of try to just give you what's going to happen here in a higher level view. So we call lookup internally inside of the GetValue function. Lookup returns 1 to us. How to do it? We just have to trust lookup function. It returns 1 for Joy. So we go to index 1. In table 1, we see that there's no blank. There's a node there, and it contains Joy, returns 22. So if you look at it, just focus on just a high level view of this. Lookup returns 1. And then we used index 1 in the getValue function. We checked table 1 index 1. If let's say it would have been a collision, we would have tried index 1 of table 2. But again, lookup function is doing all that probing for us once again. So if I were to just look at lookup function for a second, internally, remember what it does? It initially computed 4. We then go to index 4 of table 1. We had a collision. Then we try. So let me just move up my notes. Table 1 of index 4 of table 1 was a collision. We tried table 2 index 4, also a collision. So you have to apply this technique, add 1, make I++, recompute the index, and suppose this time around it computes 1 this time. We go to index 1 of table 1. There is not null, but the node there does match Joy, so it returns 1. So we get 1, and of course, in the getValue function, when lookup returns 1, we go to index 1 of table 1 and we check. If that node, so that index 1 contains a node that matches Joy. Now suppose, let's say index 1 for Joy wasn't a match. Then we would try index 1 of table 2, and then return that node's value. So that's the idea for how to get value and find. They just call lookup function. Lookup function returns a value, and then we check in table 1 and then table 2 if needed. Where lookup function is doing all that probing. It's going to compute the initial index. It checks to make sure. So when it first detects at table 1 or table 2, either a null or a match, return that index. And if table 1, table 2 at that index are both collisions, it recomputes, so it kind of probes the table and then tries different location, first table 1, then table 2, and so forth. And eventually, you're gonna either find either a vacancy or a match at table 1 or table 2, return the index. So I hope this explanation helped you understand this. Let's go ahead and now just wrap it up and go over the resize briefly, or just at least talk about it here. And of course, then just go over the main and how the input is formatted and just sort of do a test run of the actual program. Okay, so I'm going to just briefly discuss the resize function. So I kind of want you to figure out the code. I don't want to give out too much examples here, but the way it's going to work is for the resize function, you pass in some amount. So let me just scroll down the PDF to the resize function. So you pass in some amount. So basically, you can just pass in the capacity into this function, and then it's going to allocate table 1, table 2 to be capacity times amount. I guess that's a good value to use. So once you do that, once you allocate 2 tables to table 1, table 2 that are, I guess, it's going to be really, since we're going to be passing in a capacity into this function. So we call this function within our insert function. So if we insert and our table becomes 20% full load factor for either table, then what we want to do is call the resize function, pass in the amount, which will be capacity. It's going to just essentially just square the capacity, and it will allocate to larger tables, a table 1, table 2. So what I would suggest in the function resize, perhaps create 2 local pointers that point to the old tables, and have table 1 and table 2 point to 2 larger tables. And then you want to set items 1, items 2 to 0, capacity to new capacity, and then just literally go through every element of your old table one by one and just insert these into the new bigger table. So if you set your instance variable table 1 and table 2 to new sort of tables, and you assign items 1, items 2 to 0, you can call the insert function within the resize. So as long as you set your instance variables accordingly, you can just iterate through each of these one by one. And you can just call the insert function, pass in Joy 22, call insert, pass in Alice 12, and then call insert, pass in Bob and 20. So you can just, if you as long as you set table 1, table 2 to new arrays, you can just call the update insert function within resize to simply rehash all of these entries into a new position in table 1 and table 2. So I'm not going to say more. I'll let you sort of figure that out essentially, but the code is not too complicated. And once you remap everything, you want to just simply deallocate the old tables. So now table 1, table 2, the new larger tables now have, we remap these elements, and now all our nodes are in the correct position of our new larger tables. Okay, so here's an explanation for the menu type. So basically in your main, you're going to have a hash map where the key will be a string and the value is going to be this menu type right here. So I have the header file defined for you, and I have the menu type implemented as well because it's a very basic class. So you can see here, you'll be given this spreadsheet file or CSV file that contains, each row contains one menu type object. So every menu type has a name, a price, and a quantity. So here we have our famous fried oyster skins. We have our price, $14.99, and our quantity, 13. So our next item, we have kelp shake with a price of $1.99 and quantity 20, and so forth. So we have the menu type, which stores each field. We have our constructors already given to you, so you can use these when you're creating objects. And we have a bunch of getters, so you can get the name, price, and quantity. And we have a function that we can use to update the quantity, because we're going to have the user order various items, and we want to, once you order, let's say for example, if we were to order a Krabby Patty and there's 50 currently, if I order 10 of them, then I want to have 40 Krabby Patties left in the restaurant. So this update quantity function will subtract the amount. Now again, if this amount is larger than the quantity, we assign 0 to the quantity. So we don't allow negatives. We always assign 0 or the difference of quantity and amount. And we return star at this because in some cases it might be convenient to return the object, because you may use this to reassign the element in your hash maps. Returning yourself will actually make this a little bit easier to update contents in the hash map. So essentially in this assignment, you'd have to be able to read each line of input. Now, a spreadsheet file like a CSV file is essentially comma separated. So in reality, what you have is you have several lines of input. Each line, like in this case, we have item name. So if you were to actually open this up in a regular, not in a spreadsheet format, you would notice you'd have item name, comma, price, comma, quantity, then a new line. On this line, you would have the string fried oyster skins, comma, 14.99, comma, 13, and so forth. So you'd have to be able to parse this file, tokenize and separate, between commas, and you want to, of course, pass them into this constructor to allocate the object. And again, for your map, you would have to essentially call the update function. This will be your string you pass into the function. And then the value would be the object that contains these 3 fields. And you just do this one by one for each element in this file. So you first have to just simply populate your map, and you can treat this as we have our keys is our name, and the entire object will be the value it maps to. So let's go ahead and now just discuss main, how you want to set up your main file, and that should conclude this video. Okay, so to show you what's actually in a spreadsheet file, I'm going to just output it here on terminal. I think it's called krustykrab.csv. So there we are. So the Microsoft Excel presents it in a very nice way, but in reality, it's really just a comma-separated file. So the first line contains a header, so you can just sort of get line, read that line, and then just from that point on, the rest of the lines of the input file is actually relevant input. So every portion is separated by a comma. So you don't want to use a string stream because, well, it's really not the right way to actually process because it's too specific to C++. So what I would just say is use getLine and try to use string functions like find, substring, and so forth. So if you read this first line of the input, of course, the famous fried oyster skins, you want to, of course, do a find to find the comma, and you want to extract using a substring to grab the characters before that comma, and then erase and store it into a temporary variable, erase this from the string, and then process that part of the string. Call a find function again to find where the comma is located, right there, and then get the substring function to get all the characters before the comma, and you want to store it into a variable. And of course, you can use strod function to convert a string into a decimal and then store it into a decimal variable. And the remainder will be just the integer by itself. So you can, of course, pass that into a stoi function. So now you get each individual component. You can call the menu type constructor to initialize the object, and you want to insert this object into the map using this this name as the key, and then the entire object would be the value. And of course, you insert that into your map one by one. Okay, let's go ahead and now just go over the main logic. I do have it written in a PDF, but I'll go ahead and demo it here for you. So to compile, V++, it's hash map.cpp, and then we have main.cpp. Okay, let's go ahead and run this. And I'll ask you for the Krusty Krab menu. I'm going to go ahead and type it in. So krustykrab.csv. So I guess for now, just sort of disregard this. I had it output what I input because when I was constructing the input files, I had to, long story short, just disregard that. I'm going to remove this from the, when I set this up on CodeGrade. So don't worry about this for right now. But we passed in the Krusty Krab CSV file name, and we output all these to the screen. So, so we want to output them in the order they appear in the file. So you actually can maybe even have like a vector that stores the list of these item names. So you can store that list so you actually can get the correct order. And now to get the actual price and quantity, well, what you can do is if you have the list of the item names, you can pass an item name into your map, into your GetValue function that returns the menu type object that you can, of course, call the getPrice, getQuantity to be able to output the price and quantity of the item. So again, just some more hints right there. And again, you have to get the output to be perfectly aligned. I just put it like this because it makes it easier to actually read or able to, look at the output and parse it. But in your case, all you have to worry about is make sure your decimals are output to 2 decimal places. But that's rather simple to do using IO_manip. But don't worry about the set W. I'm not going to really grade you on that, but just this way it looks nice, easy to actually look at this output. Okay, so now this menu is going to be sort of, it's going to, I guess, have the Squidward theme, where we see that he's a very, very nicely mannered employee for the Krusty Krab. So we have to search and find one of our elements. Now, of course, we're going to use our hash map object. So let's say, for example, these are all funny names. I mean, hey, where is this salad? Well, oh wait, I know why. Because the salad was used when they rebranded the Krusty Krab. So never mind. They discontinued the salad. I mean, it was just really lettuce and a tomato, right? Didn't make any sense how SpongeBob set that up. So let's go with the kelp rings. So we have to search for kelp rings. I'm going to type it in right here. Now, we want to make sure our input is case insensitive. So I could, in fact, have it all in caps even, like this. And we have to be able to find this. So we would take this string, read this in from the user, and call the find function to make sure that this actually exists in our map. So find function returns true, obviously, in this case, because it would find kelp rings. So, okay, cool. So now it's going to ask us, how much of this stuff do you want? So again, Squidward, you have to learn to be a better employee, right? But I guess, we'll keep Squidward, alive through this program. So for kelp rings, well, let me see here. We have 5 of them. So if I order, let's say like 7, it's going to reprompt. And again, just disregard these numbers. I'm going to clean this up. I only did this because when I was creating the output file, I didn't want to I'd rather have my program output what I read in, so it's easier to create the input files. So I apologize for that. Just don't, I thought I cleaned this up, but it's still not cleaned up completely, but that's okay. So again, we can't actually order 7 of this item. So it's going to just basically give us this message. Okay, so I'm going to order, let's say 3. I'll be nice this time. So we output 3. Outputs a 3 there as well. So again, just disregard that. And then after this, it'll ask us, well, let's complete your order, barnacle head. So I'm going to say, for now, I'm going to say no. This will not complete my order just yet. So it's going to, again, reprompt. And again, just disregard this, this N, because it outputs what it read in. So we can see here, for kelp rings, we have only 2 kelp rings left. So I'm going to go ahead and order kelp rings once again. I'll use all lowercase this time, and it should be able to find it. And yes, it found kelp rings, so I'm going to order 2 this time. And then we'll just complete order, barnacle head. I don't know, I kind of like these Squidward's insults. It definitely keeps me in the theme of SpongeBob. So I'm going to say no, I'm not going to this will not complete my order. And notice that now, kelp rings is not going to display here in this list. So the idea is that we want to only display the elements that actually still have at least one quantity of them. So since kelp rings are sold out, it will just not display them. And also, I have this list output, so I should have said this earlier if I didn't. It's an output in the same order it appears in the input file. Now, you could just simply can store store this in a vector of strings. I'm not sure if I mentioned this earlier. If I did, I mean, I actually had to cut the video and I forgot if I mentioned this earlier, but you would just maintain a vector of strings just to maintain each item name. And if you want to get the price and quantity, all you have to do is just take your hash map object, pass in, call the GetValue function, pass in the name. It returns a menu type object, and you can call its getter, get price and get quantity, to get the price and quantity of that element. So you don't want to really maintain a vector that stores all of these. Maybe just have a vector that maintains just the names. And of course, to extract the price and quantity, just call GetValue function, pass in the item name. It returns a menu type object. And of course, you can then call the get price and get quantity to retrieve these. And again, when we want to actually update the quantity, you have to call the update function for the hash map object to reassign the value to a new value. So that's a little bit of, you have to kind of figure that out, but everything is given to you, you can use inside of menu type and so forth, but you have to figure out how do you actually update a quantity inside of the elements in your hash map. So anyway, if I were to go ahead and try to order kelp rings now, this element does exist in my map, but the quantity is 0. So still going to treat this as an output. We serve food here, as in it didn't find this element. So even though it does exist in my map, the quantity of this item is 0, so it treats it as a failed search. In fact, if I were to type in a salad, it also outputs we serve food here, because it's not in my map. So the searching function first determines if this element does exist in my map, and if it does exist, then check and see if the quantity is 0. And again, you can very easily do that. You can call the find function if it returns true, then call the GetValue function on that same item name. Call the getQuantity function. If that is larger than 0, then it's a valid item. And again, at some points, let me just go ahead and I'm going to order maybe the, actually, here you go. We have a seaweed salad. So that's kind of the same thing, right? Okay, cool. I'm going to order, say, 2 of these. And then I'm going to say yes to complete my order. And then it outputs my order total right there at the very end. So we have this menu. And again, the menu program will stop under 2 conditions. If, let's say, we decide yes, you will complete the order, or if there are no more items left. Let's say every item is sold out, then you can't order anymore. So obviously it will close at that point. The program will also stop at that point as well. So there's 2 stopping conditions here. So I do provide you also with input files as well. So let me just go ahead and just show one of these. Say cat input 01. So here's the input file I'm going to give you. So you can, of course, hard code these in, or you can actually just redirect this input if you want to test this out. So you can say a.out redirect input 01.txt, and it will feed these in to your cin essentially. So then it just kind of simulates the entire menu, like so forth. Now again, you can see here it outputs what I read in. In theory, this is not going to show 5 here if you were to not output what was read in. But I don't want to redo the video. I don't want to redo this part of the video. So, but the idea here is it will just simply, you can just feed in the input without having to interactively do it. So if you want to just test out your input and make sure that your final cost is correct, and of course if these quantities are all matching your output and so forth. So anyway, that's sort of the I guess the video for this program. So hopefully this helped you understand it. So I guess that's it for now. So take care till next time, and happy coding.